I'm going to start us right here. And today we're going to talk about research methods in child development. There's going to be two presentations about research methods. Today, I'm going to talk mostly about quantitative methods. And what that means is quantitative means you can put a number to it. So you can assign a value to information. And information is kind of the key. You'll remember in a scientific method, you have a hypothesis, something that you can test. And so you gather some observations or some data so that you can test those hypotheses. In child development, there are different ways that we can collect this information. And this data can really be anything we can measure. So it could be opinions, beliefs, or it could be physiological measurements like blood pressure. It could be anything that we can assign a value to. So the two broad categories that are important in child development are observational methods and naturalistic observation. So we can observe in a controlled laboratory, or we can observe out in a natural setting. Both of those have strengths and they both have drawbacks. A laboratory observation has the strength of you're in a controlled situation. Everyone is observed in the same surroundings. You can control the time of day, you can control the amount of light in the room so that every observation between your different participants is in a similar setting. The downside is it's sort of an unnatural setting, and people may behave differently than they would behave in the real world. And that's why we sometimes use naturalistic observations. This is when the researcher goes out and observes in we call it the field. They observe in a real world setting. It might be a school or a playground or some place that families interact. In a naturalistic observation, the observer doesn't control or manipulate the setting. What unfolds is what naturally would unfold. The drawback there is that lack of control. So somebody might want to get up and leave where you're observing them, and that's fine because that's a natural setting. But you have no control over that kind of change in the environment. This is an example of why naturalistic observation is important when we do research with children. This is a study from the Natural History Museum of the Smithsonian. And in this study, the researchers were interested in how parents talked about the science related concepts of a fossil display, of a, a museum kind of display where people could just come and go on their own. So the researchers held a clipboard and they looked like they were making notes about the display itself. But what they were really watching and listening to was the ways that the parents talked about the display with the child. And what they found was that parents of boys talked about the science of the display almost 30% of the time. But parents of girls, it was only a little over 5% of the time. So there was a big difference in how parents framed that display depending on the sex of the child. Now imagine if those researchers had instead conducted a laboratory observation. They would have had more control over the situation, but the parents would have realized they were being observed, and so they might have changed. Imagine if they brought them in the lab and said, here's some models of dinosaurs. We just want to see how parents and kids talk about these dinosaurs. Well, if they were on sort of notice that they were being observed, their behavior might look very different. There are other ways that we can collect data with children as well. One thing that you might see is called a case study, and this is a really in-depth look at just one particular individual. So it might be observations over time, collections of information about that child. That has a real strength of getting a lot of detail about one particular individual. But the downside is you never know if what you observed in that one person can generalize to other people. The word generalizing means, can I take what I learned in this setting and apply it to all the other settings? And because each individual is genetically unique, we don't know how much we can apply that information to other settings. So you see case studies more of assessments about a particular child. You see them sometimes for medical studies and those kinds of things. Another thing that a case study can be useful for is to be when something is so unique that happens, that it might tell us about, give us some insights into more typical situations. So what's it like to be a, uh, a conjoint twin who is separated from surgery, and now you have a separated sibling? Well, that's a really uh, unique kind of situation, but it might tell us something about sibling relationships in general. But again, it's difficult to know how much of that you could generalize because that situation is so different. Other ways that we collect data include surveys and interviews. Surveys are written questionnaires, and you've all taken surveys. They might say, this is a little bit like me, and this is a whole lot like me. Those are called Likert type skills. An interview, in a lot of ways, is a survey that's conducted live. So it's, instead of answering the paper or the computer screen, there's an interviewer there, and that has the benefit that the interviewer can ask follow-up questions or sort of shape the interview to each participant. In either case, of a survey or an interview, it's important that the questions are clear and that the questions are unbiased. You have to be really careful and watch out for sort of double barrel questions where the answering the question assumes that you've that the first part is true. Isn't it terrible that all the children aren't learning anything in school today? Well, that's a really loaded question, right? So the questions have to be unbiased and clear. Another way we collect data is with standardized tests. Standardized tests means that the test is offered in the same format, that everyone gets the same questions, and those can be standardized by comparing the score that one person gets on the test to the score that everybody else gets on the test. So you can standardize the raw score with a percentile score. Other ways we get data are psychophysiological measures like an MRI or an EEG. You've seen uh, images of the brain that show which area is active by different colors. That's an MRI. EEGs are those readouts that show the electrical impulses that our brain is displaying. Also, things like heart rate, blood pressure, all of those could be physiological measures. Okay, so that's how we get the information. The next step is, what do we do with those data when we have them? And when we talk about quantitative designs, those designs where we can count or put numbers or values onto our data, there are two main types. So if you think of a level of quantitative, underneath that is descriptive and inferential. So first, let's talk about descriptive. Descriptive research, the goal is to observe and record information. So descriptive designs address topics such as who or what or when or where. They describe how many, what percent, the average, the minimum, the maximum. What descriptive designs and descriptive statistics do not do is they do not try to look at how is this variable related to that variable. If this variable changes, does that variable change? Instead, this is the count. What percentage of high schoolers in Tennessee pass their reading exam? That's a different question than what is associated with passing the reading exam and what's associated with not passing the reading exam. So what descriptive statistics do not do is try to make predictions. And these are examples of descriptive statistics. So things like the mean or average, the standard deviation, which is the average distance between scores, the total count of people, the median, minimum, maximum. So when you see like pie charts that have percentages or bar charts that have frequencies or counts, These are descriptive statistics. So this example of single, married, widowed, and divorced is just giving us a count in this particular population or sample of what those percentages are. It's not saying, well, the people who are single are more likely to do this, or this was associated with people having a higher probability of being married. Inferential designs do that second step. They go a step further and say, if I know about this variable and I know about that variable, is there any association between the two? If one goes up, does that have an impact on the other? Or does the other one also go up or down? So in inferential designs, researchers use statistics to think about probability. If this happens, what's the probability that that will also happen? Is it just chance, or is it unlikely that this would just be chance? Now, under inferential designs, there are two main categories. So we have quantitative, under quantitative, we have descriptive and inferential, and under inferential, we have correlational and experimental. So let me talk about correlational designs first. In correlational research, the goal is to examine the strength of an association between two or more variables, two or more events, two or more characteristics, any of those types of variables. The question that's asked is, one of these variables change, how likely is it that the other one will also change? And statistically, this is computed with what's called a correlation coefficient. And the correlation coefficient is the degree of association between two variables. So say one variable is X and one variable is Y, the correlation coefficient tells us how closely associated they are. Now, this is the important part, and this is where critical thinking comes in. Correlation does not mean causation. And I'm going to say that over and over for the next few minutes. Just because variable X is correlated with variable Y, it does not mean that variable X causes variable Y. Now I have here kind of a axis between X and Y, and I'm going to instead share a whiteboard like this. And what I'll do is I'll just draw this down and this over, and we'll treat this as our x-axis and our y-axis. And let's say we went outside today and people were in a good mood to talk with us, and we did some assessments about, we asked people some survey questions, and we said, hey, what size is your shoe? And we plotted their shoe size across the x-axis. So bigger shoes were on this side and smaller shoes were down here. And we measured their height and we plotted that on the y-axis so that more height was up here and less height was down there. And we took our data and we said, okay, our first person they have a big shoe size and they're very tall. And the next person is a little bit like this and a pretty big shoe. But there were also some people that had smaller than average shoes. And there's one person who had a big foot, but they weren't there. And eventually, when I get enough of these data, I start to see an average kind of line. And it's going to look like this. And this line goes up. So this is what's called a positive correlation. The positive correlation happens when variable X goes up, variable Y also goes up. But it could be something like this. Let's say while we were there, I'll give you another example of a positive correlation because I just thought of an idea. So while we're there, we'll ask them what their GPA is, and we'll put that on the y-axis, and we'll ask them how many hours they study, and we'll put this on the x-axis. And some people studied more hours and they had a higher GPA, and some people studied lower hours and they had a lower GPA. And we find our positive correlation. Higher GPAs are associated with more hours studying. But while we're there, we also asked them, how many beers do you drink every day? And we found that there were some folks who, let's say we put our GPA on this line here of Y, so higher GPAs up here and lower down here, and this is beer drinking on the X, so more beer drinking and less beer drinking. And we took our stamp and we found that somebody drank a lot of beers, but they had a very low GPA, and somebody drank no beers and they had a high GPA, and some drank a little bit and their GPA was still pretty good. And then there were some folks who had a low GPA, but they never touched the stuff. And we end up with a line that does this. Okay. This is a negative correlation. What this means is when variable X goes up, variable Y goes down. Now, our correlations are measured from +1 to -1. So a perfect positive correlation would be 1.0. A perfect negative correlation would be -1.0. And what that means is in this perfect positive correlation, oh, that's weird. Okay, I'm not going to worry about that. If it was a perfect positive correlation, our line would be just straight like this. Every time X went up 1 unit, Y would go up 1 unit every single time. There would be nobody falling off that. It would be a perfect correlation. A perfect negative correlation would be like this. Every time X goes down 1, Y goes down 1. But even then, even with that perfect correlation, we don't know that X causes Y. Remember that drinking beer and your grades? Well, it could be the opposite. It could be that people who have bad grades just give up and go drink the beer. And so it could be that bad grades cause drinking beer. Or it could be something else entirely, like depression. It could be that people who are more depressed drink more beer, and people who are depressed get lower grades. So it looks like there's this link between drinking beer and grades, but really it's the fact that both of them are linked to depression. And so in that example, this is called an extraneous variable or a variable Z, something else that you didn't control for that's causing the change in both X and Y. And let me show you one last example here. It could be, so we asked them their shoe size and we asked them their GPA. So let's chart those together. Let's say this is their shoe size and this is their GPA. And there was somebody with a big foot and a good GPA, and a small foot and a high GPA, a small foot and a low. And overall, we get just this sort of random, and there's really no association between shoe size and GPA. And then if we were going to draw our line, that average of that line, it would just be this flat line across here. And so in that case, our correlation is 0. So remember, our correlations go from positive 1.0, and somewhere in the middle, our correlations like 0.5, 0.3. And you can see this is the slope of that line. So, and then down here, we have like -0.3, -0.5. put 0.0, that's no good. All the way to that perfect negative correlation of negative 1.0. So this is that perfect positive. Change in X is a direct change in Y. This is that completely flat where there's no association between them. So a correlation of 0.5 means there's a steeper slope. So it means there's a stronger association between X and Y than the correlation of 0.3. But all the positive and negative sign does is change the valence, change the direction. So a correlation of negative 0.5 just means that when X goes up, Y goes down. That's a stronger correlation than the correlation of 0.3, even though it's in the opposite direction. So it's the absolute value, the closer you are to either positive 1 or negative 1, that tells you the strength of the association. And no matter that strength of the association, there's no causation there, okay? So let me share that PowerPoint back to you guys real quick. All right, so that's correlational designs, and the purpose of this slide is to just remind you that there's no causation there. So the researcher observed a correlation between permissive parenting and children's self-control. So as permissive parenting went up, self-control went down. Now that could be because permissive parenting causes children to have less self-control. The parents are permissive, the children never have to practice self-control. It could go the other way. It could be that children who have lower levels of self-control, the parents experience that, they observe it, and so they say, hey, I'm going to back off a little bit, and they become more permissive. It could be a child that's driving that. Statistically, both of these possible explanations are just as valid as the other. The difference comes in how we interpret it. It comes from the theory. It could also be that something else, that extraneous variable Z, is causing both. So genetic differences, because the parents share the same genes as the child, or culture or poverty, that could cause both permissive parenting and lack of self-control. And so what looks like a correlation between the two is really because they're both linked with something else that we didn't assess. And that's one of the limitations of correlational designs, is because you didn't control for that other explanation. You didn't have a way to account for that alternative explanation. So you never know if you have a causal relationship. And that's where the strength of research, of experimental research comes in. In an experimental design, the researcher manipulates one of the variables. In complex experimental designs, it could be more than one variable. Everything else is held constant. So the idea here is to control for all those other possible explanations, to eliminate those variable z's so that you're only talking about variable x and y. And the way they do this is through an experimental design that involves independent and dependent variables. Independent variables are sometimes called the experimental variable. The dependent variable in a simple research design it could be thought of as the control group. So I'll give you an example of an experimental design. In this design, the researchers were interested if aerobic exercise during pregnancy predicts newborn babies' breathing and sleeping patterns. And so the participants were randomly assigned. Some were assigned to a experimental group that received the aerobic exercise, and others were assigned to the control group that didn't do the exercise. And after the babies were born, their breathing and sleeping patterns were assessed. So in this example, the experimental group versus control group is the independent variable. This is what was manipulated. Some experienced this variable, some experienced that. The dependent variable is the newborn's breathing and sleeping. This was assessed to see what impact the difference in the independent variable had. Now, this is the most straightforward example of an experimental model, but you can imagine we could have 3 or 4 different experimental groups, maybe just a little aerobic exercise, uh, and we could look at those kind of variations. But in the simplest term, you have an experimental or a control group. Now, if the researchers really did hold everything else constant and they controlled all those other explanations, and they found that for the babies whose mothers were in the experimental group, they had improved breathing and sleeping patterns, then they could conclude that aerobic exercise during pregnancy contributes to more positive breathing and sleeping after birth. Now, again, that's assuming that they really were successful in controlling all the other variables. And one of the words that's important is this randomly assigned, because it could be that there are differences in the people who are in this group and who are in that group that weren't caused by the aerobic exercise. It could be that these people were just different. And random assignment is the way that researchers try to wash out those differences that people bring with them. So say that instead of randomly assigning them, maybe the researchers put up an advertisement sign in uh, the gynecological office when the women would come in for their assessments. There was a recruitment, and they would say, "Hey, come be in our study about aerobic exercise," and they said, "Okay," and they said, "Okay, which group do you want to be in, the aerobic group or the control group that doesn't do exercise?" And they let the mothers choose which group they were in, and then they assessed the breathing and they found that difference. We couldn't really be satisfied that that was causal because we don't know if the mothers who chose the experimental group were different from the mothers who chose the control group right from the beginning. It could be the mothers that really liked exercise all joined this, and so they just were more physically fit to begin with. Or it could be the mothers who smoked cigarettes said, "No, I don't want that exercise," and they joined the control group. So you've left open competing hypotheses by not controlling that assignment. So it's important, if you're going to conclude uh, causation, to randomly assign people to the treatment or control group or to the different levels of the independent variable. This is another example of an experiment. This is a researcher named Albert Bandura. You'll hear about Bandura again next week. We talk about theorists. Bandura brought children into a laboratory setting and showed them movies of, well, in the experimental group, the movie was a model. Another child entered a playroom, and in the playroom there was a Bobo doll, like an inflatable doll with a sand bottom. And in the movie, the the kid with the Bobo doll just goes nuts on it. He's beating it and he's pounding it and kicking it and throwing it around. The control group, they didn't. They just saw a movie about some kids playing. They didn't have that aggressive model. They saw a movie, but they didn't see that aggressive models movie. For the dependent variable, this is the independent variable, whether they saw the aggressive model or not. For the dependent variable, their behavior was observed as they themselves entered a room that had a Bobo doll in it. And sure enough, the children who were in the experimental group who saw the aggressive model were more likely to be aggressive with the Bobo doll in real life. The children in the control group that didn't see that, when their behavior was observed, they weren't more aggressive with the Bobo doll. Now, Bandura controlled for everything else. They were in the same setting, it was the same time of day, and the only difference, they saw a movie, but the only difference in the movie was the aggressive models. And because that was the only difference between the independent variable of the experimental control group, then the difference in the dependent variable, these children were more aggressive than the children in the control group. That could safely say was caused by viewing the aggressive models. Another factor of research that's important for developmental studies is the time span. How are we asking questions about the onset of different developmental traits? The most commonly used approach is called a cross-sectional approach. And what that means is that individuals of different ages are compared at one time. So say I want to know about my spelling program. Does my spelling program uh, work for fifth graders, and does it work for third graders? And I want to assess this. I go to a school and I get a group of third graders. I give some of them my treatment program. I don't give it to some of them. And then I give them a spelling test. I get another group of fifth graders and I do the same thing. And I can say at 3 years old, this happens. And at 5 years old, that happens. And that's what the cross-sectional approach is. I have different groups at different times. I can show you better on this. Yeah, I'll tell you first. A longitudinal approach, I follow the same individual over time. And this could, so the kids that I gave the spelling study in third grade, I come back in 2 years and I give it to them again in fifth grade. And I see if they perform differently. A cross-sequential uses some aspects of both cross-sectional and longitudinal. So this picture just shows us an example of cross-sectional research. So here, this was done in the year 2000, and they wanted to compare participants of different ages. So in the same year, they went and got one group of 20-year-olds, one group of 40-year-olds, and one group of 60-year-olds. Now the problem is we don't know if these groups were different to begin with. And there can be cohort effects. That means that something happened in the lives of these 60-year-olds that didn't happen in the lives of these 20-year-olds. So, for example, the 60-year-olds, they might be able, in 2000, they might have been able to remember something like the Vietnam War. This group here of 40-year-olds, they wouldn't. And this group of 20-year-olds, they've really only experienced war. The country's been at war their whole life. So the perceptions about war would be very different for these three groups. So a way to take control of those cohort effects is a longitudinal design. And here you would interview one group of participants when they were 20. You'd come back in 20 years and talk to them again. You'd come back in 20 more years and talk to them a third time. And that way, you know, if there's any changes, it's related to age because you've controlled for those cohort effects. The problem is it took you 40 years to find out. And most of us can't wait around 40 years for our research. And it was also bad because when I went back 20 years later, some of the people were gone. I couldn't find them. And I don't know now if the people who are gone, if there's something systematically different about the people who are still there. So I'll give you a different example. Let's say our study is about children and the effects of divorce, and I want to know if it's still has an effect 3 years later. And so I come back in 3 years, but I can't find some of the kids. Well, maybe those kids, there's something different about them. Maybe they all moved away because there was more conflict in their household. So maybe their outcomes would have been different. I have this question now I can never answer. So that's one of the downsides to what in other ways would be the gold standard here of longitudinal research. And that's what cross-sequential research designs try to address. So in this kind of simple model, they gave people's names here. But in this year, we had two people, Anne and Betty. And the next year they came back, or 20 years they came back, and they added Carla. So between 1950 and 1970, this is longitudinal, Anne to Anne and Betty to Betty. But within the year of 1950, they had a cross-sectional Anne to Betty. And within the year of 1970, they had a cross-sectional Anne to Betty to Carla. So these diagonal kinds of lines, these show the longitudinal study, and these horizontal lines, or I'm sorry, these vertical lines, they show the cross-sectional study. So that way they have some data this first year, but then they can come back and add some longitudinal questions later. two more important words and we'll be done for today. One is reliability. Reliability is how your measurement device is, does it always give you the same measurement? And that's really important. I'll give you an example. When I was in college, my car was this old Pontiac Sunbird. Some mornings I'd go out and turn the key and the engine would start. Some mornings I'd go out and it wouldn't. It was not reliable. Another example, say you have a bathroom scale and one morning you get on the scale and you weigh 200 pounds and you get off the scale and you get back on and it says 195 and you get off and you get back on it says 205. Well, your scale isn't helping you very much because it's not reliable. It's not giving you the same measurement each time. Now, in the physical sciences, reliability is kind of easy. So if my measurement device was a scale like this, I could put on the scale of known weights and see if it always gives me the same measurement, or I could compare one scale to another and calibrate them. But when we're investigating people, it becomes a little more complex to assess our reliability, but it's just as important. So, for example, there are times when we don't want people to always give us the same answer. Some of you took the ACT more than once, and you didn't take it the second time hoping that it's going to give you the same score you got the first time. Well, the ACT is reliable, so we want it to give us the same scores every time, but you took it hoping that you learned something the first time that's going to help you score better the second time, right? So those scores would change. Well, for that reason, we have things like test, retest reliability. So uh, I maybe I compare the first half of my test to the second half. It's called a split half. So that in the same time that you're taking it, I'm assessing reliability. Or I compare the odd numbers to the even numbers. Or I compare one item to every other item. Does it give us the same kind of outcome? And a lot of research with children is observational, and I mentioned that earlier. In observational assessments, the equivalent of the scale, it's not a questionnaire. The equivalent of the scale is the person who's doing the observing, the observer. And they are reliable if what one person observes is the same thing as what another person would observe in the same situation. And so you can assess that inter-rater or inter-observer reliability by comparing one person's observations with those of another to see if they're getting consistent kinds of measures. The second big concept is validity, and reliability and validity do a little dance together. Validity means that your instrument, your measurement, is really measuring what you think it's measuring. So again, this is easier in the hard sciences. If you want to know how much a rock weighs, you put it on the scale and you weigh it, and your measurement is valid. As long as your scale is measuring correctly, you are actually measuring the weight of that rock. Well, in social sciences, it's not always that clear cut because sometimes we're measuring things that you can't just scoop out. How aggressive was this child? How much love is there between the caregiver and the child? Well, those are things we can't just measure with a ruler or pour into a measuring cup. And so we've got to first decide on how do we define aggression or love, and what the way that one person measures that may not be the same as another. And so we've got to make measurements that have face validity. They look like they're measuring what they say they are. But we can also talk about things like criterion validity. We think this is valid because it is associated with the things it should be associated with, and it's not associated with the things that it shouldn't be. And that's discriminant validity. An example of that is the ACT test. Um, the ACT test is a measure of to predict how well will somebody do in college. Will they succeed in college or not? And the ACT test has some validity because it predicts the thing it's supposed to. It predicts how well people do in school. It's not a perfect prediction. You all know people that struggle with the ACT who do great in college, and you know people who uh, did great on the ACT and flunk out of college. But across the whole population, there's a correlation between doing better on the ACT and doing better in college. And so in that way, it has some